Okay, next we have Sarah Greer from Massachusetts Institute of Technology. Her field is mathematics and computational science, and she has done her practicums at Los Alamos National Laboratory.
Thanks for the introduction. So the title of my talk is Superresolution with the Zero-Phase Imaging Condition, and this is work I've done in collaboration with my PhD advisor, Laurent Demenet at MIT. So I'm going to start with a summary of what exactly this talk is about. So my area of research interest is in the field of seismic imaging, which are, I guess, kind of classes of methods that are used to, find subsurface structure in the Earth. This is useful for fields like, I guess, in oil and gas exploration, if you want to find where oil deposits are, or things like carbon sequestration. So I'm going to be talking about something similar to this model on the right. If you can imagine, if this is the surface of the Earth, what this is a two-dimensional cross-section showing kind of the subsurface of the Earth. In a seismic survey, you typically have sources and receivers that are, I show here, on the surface of the Earth. And kind of these sources, what you're using is sound waves, essentially. So this kind of source you would have here could be something like a sledgehammer hitting the ground, and it would propagate energy into the subsurface, and that would reflect and refract off of the subsurface interfaces and arrive back at this receiver array here. And my contributions, or what I'm interested in, is specifically looking at things, I guess, called the imaging condition, which more or less is kind of the operation or the mapping of the data recorded at these receivers to an output image, which represents the subsurface structure. Specifically, what I want to talk about today is something called the zero-phase imaging condition, which I'll introduce, which allows for resolutions greater than that ordinarily expected using standard imaging techniques, using a standard imaging condition. And using this, I'm successfully able to resolve the location of specific scatterers in the domain and increase imaging resolution in more complex media. So I'm going to kind of, in this presentation, go back and forth between comparing standard imaging techniques with the zero-phase imaging condition and how it improves in certain ways. So I just want to start with an example of what we're looking at. So on the left, we have a velocity model. On the vertical axis is depth. The horizontal axis is spatial location. So this is a 2 kilometer by 2 kilometer domain. There's an array of sources and receivers on the, on the surface of the domain. And what this, the model is showing is velocity of the underlying rock. And what I'm going to, every model I'm going to use in this presentation is going to be a model with a constant velocity background medium and a single scatterer located in the center of the domain, just for simplicity's sake, and that's where the theory works. That can be expanded, but I'm going to present the theory for a single scatterer. Using standard imaging techniques, we're going to get an image that looks like this, which is kind of a blurred representation of the original scatter located in the center of the domain. So it is a lower resolution result than the standard velocity model. With the zero-phase imaging condition, we're able to get a scatterer that exactly lines up with the location of the scatterer in the subsurface. So I want to start by introducing what an imaging condition is. And because we're looking at wave propagation, it's more intuitive to think in the time domain. Although the zero-phase imaging condition is done in the frequency domain, I'm going to start with introducing what a standard imaging condition looks like in the time domain. So it's this equation here. So this image is a function of x, is essentially a time interval over time, of the product of two different wave fields. So this right here, this u0, is called the forward wave field. This q is called the adjoint wave field. I'll introduce those a little bit more in a little bit, but just know that it's kind of it's an interval over time of a product of two different wave fields. What exactly does this look like? I'm going to show you an example with a source located in the top center of the domain and a scatterer located in the middle of the domain. So what I have here is an animation. This imaging condition works. So if this on the left is our domain of interest, what I'm showing you here is the forward and adjoint wave fields. So our source is in the center of the domain, and this wave that's spherically spreading out from the source location, I'm going to let it run again, but I'm going to follow with my cursor. This one right here is the forward wave field, and how you get that is you assume a background medium as an initial guess for what you think the model will be, and you propagate a wave through it. So in this case, our background medium is a single velocity, so it's just going to be a spherically spreading wave. This other wave field, cursor, that comes up from the base and kind of collapses at the location of the scatter right there, and then arrives back at the receivers or spreads across the receivers. That's the adjoint wave field. I'm not going to talk about how you get that because it's kind of an entirely different complicated process, but just know that the data that you receive at the receivers is embedded within the formulation of the adjoint wave field, and it's also found along with the imaging condition itself with the adjoint state method. So this figure on the right, what I'm showing is this I of x, this image of x as an interval from 0 to t at that specific time. So what I'm trying to show is that when the forward and adjoint wave fields coincide, both in space and time, that's where there's energy produced in the image. So let this run again. But right here, where they coincide, is where the scatterer lies, and that's what the image is produced at with a single source. So that was in the time domain. We are more interested in looking at the frequency domain because that's where we can modify with our zero-phase imaging condition. So the imaging condition in the time domain is this, and it's effectively, for the most part, the same as the standard imaging condition in the time domain, except we're integrating over frequency, over omega, instead of over time. So instead of solving the wave equation, which is in time, we're solving the Helmholtz equation, which if you were to think in this case the solution of the Helmholtz equation, to get that from the solution of the wave equation that I showed on the previous slide, it's the Fourier transform across time for every single spatial location. It might provide more intuition as to what this equation means, but it's almost the same. It's still integral over frequency instead of over time. So the zero-phase imaging condition essentially states that this scatterer exists where the phase of the product of these two wave fields is 0. There's theory behind this I don't have time to get into, but I'm going to show you visually that this makes sense and that this works. So where is the phase 0? What I'm going to show you is the phase of the forward wave field here. I'm going to show you the phase of the adjoint wave field here, and the phase of the combined product of the forward and the conjugate of the adjoint wave fields here. So these plots I'm going to show you have, in the color bar, is angle, it's phase. It goes from negative pi to pi. And this is the forward wave field that I'm showing you first. And you can see what it looks like is these concentric circles. But note this is wrapped phase, so if you were to unwrap it, it's just this linearly increasing, I guess, in a circle, but increasing away from the top center location, which is the location of the source. So you can think, and also it's sweeping through frequency, so I'm going from like negative 300 to 300 in omega. So you can think of the phase of the forward wave field kind of being analogous to travel time or distance, in this case from the source location. Now I'm going to show you the phase of the adjoint wave field, which is very similar to the forward wave field, except its centered location is at the location of the scatterer. It's got concentric, I guess, for the most part, concentric circles. There's this arc here that's from an artifact from the fact that we have sources and receivers located on the surface, so it's kind of biasing that direction. But for the most part, you can think of it as travel time as a distance from the location of the scatterer. And when you combine the product of the forward and the conjugate of the adjoint wave fields, and we look at phase, we get this interesting pattern here. But one thing I want to point out is if my laser pointer is shaking it around, it's right there. That's where the scatterer is. If we're looking across frequency, the only location in this entire area, I guess, where the phase is 0 is at the location of the scatterer across all frequencies. So an even stronger condition than that is that the derivative of the phase with respect to omega is 0, because across all frequencies at the location of the scatterer, the phase is 0. So utilizing this assumption, I guess, we can create a new imaging condition, which is here, which this is the exact same thing as the standard imaging condition in the frequency domain, except we have this phi operator here, which essentially acts as a mask. It looks at the phase difference between the forward and adjoint wave field and tries to, it says something like, if the phase is 0, the derivative of the phase to make it 0, we want that in the image. If it's not, if it's further away from 0, we don't want that in the image. And you can kind of tweak that a little bit, but that's for the most part what this operator is doing. So I want to show this example again. On the left, we have our velocity model, a single scatter in the center domain. In the middle, we have our standard image. And on the right, we have our zero-phase imaging condition. So how does noise affect the result? This is a very, I guess, important question in super-resolution, and this is where I'm going to address the high-performance computing part of this talk. What we believe is that the resolution limit of a scatterer is linearly dependent on the noise level. So we can show this with numerical experiments by adding varying amounts of Gaussian noise to the data and then measuring the resolution of the scatter as a function of tau res, which this tau res here I define as how selective you want that mass to be. Do you want a very small tau res? That means that you need the phase to be exactly 0. If you increase your tau res, you're being less selective and you're allowing more information into the image. So I'm going to show this example with this kind of velocity model. Note that this is a zoomed in version. It's only a 250 by 250 meter domain, while previously it was a 2 kilometer by 2 kilometer domain, so it's a little bit zoomed in. But we can end up with a plot like this. On the x-axis, we have our tau res, how selective we want the imaging condition to be. On the y-axis, we have R, which I define as a measure of how large the scatter is. On the right, I have the image. I'm gonna go through all these data points on this plot, but we have the image with that specific tau res and R. So when you have a tau res that's really small, we're following the green star here. When we have a tau res that's really small, we're being too selective with the amount of noise that we have, because there's noise added to this data, and we're not able to resolve the image because there's too much noise. So with a too small tau res, all we're getting is like junk data, essentially. It's gonna be junk because there's too much noise. And then when we get to the right tau res, we're able to perfectly super resolve. In certain cases, we're able to super resolve the scatterer. We can increase our tau res, and that we're becoming less selective in how much we want to add or contribute to the imaging condition. And it produces something that kind of approaches the original scatterer. So this is, once we reach this kind of flat part, that means that it's reached the original regular imaging condition. I'm gonna go back to show that again, but sorry. So with a very small tau res, we're being too selective, there's just noise. And then we were able to super resolve. And as we increase our tau res, we're getting more and more similar to the regular image. So we can run that a bunch of times with a bunch of different noise seeds for a single noise value, get the mean of that. Run that for a bunch of different values of noise, of sigma. So, and what we're interested in is seeing what the minimum value is, the minimum resolvable value. So how small are we able to get our how large the scatter is as a function of the noise that we put into it. So that gets us a plot that looks something like this. On the x-axis, we have sigma, the amount of noise we add. On the y-axis, we have R, the size of the scatter that we're able to resolve out of that. The green points represent specific data points. The red dots represent kind of the bin of each noise value. And we're able to get a linear fit quite well, which is what lines up with the theory that I'm not presenting the theory, but this lines up with the theory. A few things to note. Up here, I plotted what the standard resolution of the standard imaging condition is, which is quite a bit higher. We're able to get a resolution greater than that. Another thing to note, I know this is going to be asked if I don't address it, this is numerical grid spacing. That's why there's kind of a shelf there and points. We're not able to resolve below numerical grid spacing in this case. So I talked in this talk so far just using single scatterers. We can expand this to more complex geometries, similarly to the ones shown here. So I'm not going to talk about how we get that because that's a whole other story, but it can be done. It can be expanded to certain, a bunch of asterisks added there to certain geometries. But this is what our standard image looks like this on the left. It has some, it generally follows a structure. It has some artifacts around up here that are not desirable in an image. Depending on how we define our tau res, this is like a less selective tau res. We're able to just remove the artifacts. It does remove some parts of the data where there's poor source receiver coverage. We can be more selective with our tau res and get more of the location of this exact interface, depending on how selective we get our tau res. So we can kind of modulate this input tau res to affect the output resultant image. So in conclusion, I introduced the zero-phase imaging condition, which essentially states that in the imaging condition, the derivative of the phase with respect to omega of the product of these forward and the conjugate of the adjoint wave fields is 0 at the location of a scatterer. Additionally, the resolution limit of the scatter is linearly dependent on the noise level. And this can also be expanded to more complex geometry, like I showed, with a bunch of caveats there, but it can be. So finally, I'd like to thank the Department of Energy Computational Science Graduate Fellowship. This has been an incredible opportunity I've had to work on this research. In addition to that, I didn't talk about my work I did at Los Alamos National Lab, but through the fellowship, I did 3 practicums at Los Alamos National Lab, working with Dan O'Malley and Yuzo Lin, and I had a great time and learned a lot in the practicums. And of course, I'd like to acknowledge my PhD advisor, Laurent Demenet, for his help in this work too. I'll take any questions.